Hello. So my big question on today's one was our motivation level, and I would like to share with you that your average motivation level is a 2.966. I don't want to round that all the way to a 3 because that might be a little too much, but it's the 6 repeating, so by rounding rules, I'd have to say it's almost a 3, which is pretty good considering everything that's going on. To have motivation level of a 3 and in betweeny, I will take it. It's not directly in the 2s, just about a 3. We don't have everybody reporting yet, but Aryav, he has submitted his stuff, so I considered it. We got most people done because he might procrastinate the most, or just take naps longer than he anticipated, like 3 hours longer than his half an hour. So you're welcome for that. So that's not bad. I'm going to find more about the AP test tomorrow night. They're going to post some things out, and then I'm sure things will hash out. So hopefully I'll have some more. Maybe on Friday I can tell you about what the AP test is kind of all about, what we're thinking it's about. That's coming from the AP Guru guy. As for my meeting today about grades, more to come on that. I am not going to say anything yet because the school is going to officially put out something at some point in time. So that's all I'm going to say about that. Today we're going to talk about quite a few of them: 4, 6, 7, 9, 10, 11, 12. Those are the questions from Unit 3. Unit 3. Right? Right. 4. Here we go. Okay. So if you don't need help on this, then you don't have to listen. That's totally fine. So here's the numbers we're going to start with. Okay, so I'm going to start with number 4. It was one of the top that missed. So I had the top that missed were number 4, 10, and 12. So if you were in that list, you were not alone because most people missed those ones too. So this was a hot one to miss. Most of the people wanted to say C for number 4. Strength of intermolecular forces. If I look at all the choices here, I can see that they're all nonpolar. Nothing screams out anything polar because they're all the same substances each way. So if they're all nonpolar, then I have to start thinking about, okay, then all I have is London dispersion forces. And the thing about London dispersion forces is we have that thing polarizability. That's when you have a really fat molecule, and it could have a chance that the electrons happen to be on one side versus the other over here, versus over here it could be happening too. So you have a lot of chances that you could have a polarizable section of the molecule. Now these ones aren't super big, but then we also talked about the more electrons you have, the greater probability that you could have an unequal distribution of electrons on one side or the other. That's what makes it more polarizable. So most of us wanted to say C. I'm not sure why we're picking fluorine. I don't have like a guess for that. But bromine is the most massive according to the periodic table. 2 bromines together is more massive than any of these other ones. Thus, the larger it is in molar mass, the more polarizable it is. The higher the intermolecular forces. A higher intermolecular forces would mean you will have a higher melting point because it will take a faster molecule to be able to break that intermolecular attraction in order to actually melt. Or when melting, you don't fully break it, you're just loosening them. That is number 4. 5 was the requested one. So 5, it says there's some key terms in here. Equal masses is a key term. Ideal gases is a key term, and rigid container. So this first sentence is just full of key terms. So if we look at the answers here, we're trying to look at which of the following statements about partial pressure of a gas X is correct. We know nothing really about X, Y, or Z, other than they are different gases. So basically they're different. So A was a common answer that you might have said that was wrong. It is equal to 1/3 the total pressure. We can't say that because it's talking about masses here. If we had 1 mole of each of them, then you could say it's equivalent to 1/3 of the pressure. The pressure of X would be 1/3 the pressure of the total, if you're looking at moles. But this is talking about masses. And masses doesn't tell me how many particles there actually are. So that doesn't work. B doesn't work because it depends on intermolecular forces of attraction. Right here we're talking about ideal gases, that ideal word. So therefore we can't have any differences in pressure. Every gas will act the same as long as you have the same number of moles and the same temperature. So B doesn't work because they're all ideal, and no ideal gases will have intermolecular forces. A and B were the only other answers. D and E, nobody said. C is the best answer because it depends on molecular masses or molar masses. In other words, if I have 1 gram of each of these, then I can use the molar mass to determine how many moles I have of each of those. And the mole will tell me the pressure. So that's by that one. 6. Okay, let me see for 6. Okay. So here, a rigid metal container contains oxygen gas. Which of the following applies to the gas in the tank when additional oxygen is added? So if you said A, the volume of the gas increases. Here, a key term is the word rigid. If you ever see the word rigid, that means it can't expand. It can't get bigger, it can't get smaller. It's just one set size, kind of like a metal gas can. So that's why the volume can't change. B, the pressure of the gas will decrease. Well, if you add more oxygen, the pressure shouldn't decrease, it should increase. So that doesn't work. C is the correct answer. The average speed of the gases remains the same. Speed of the molecules is determined by temperature. And here it says constant temperature. If you see the word constant temperature, you know the speed's the same. That could be an easy answer. They really like to do that a lot, to be honest. Like to deal with temperature and speed in some way, constant temperature, but they like to hit that one. D was another answer that people had said. The total number of gas molecules remains the same. That can't be true because we're adding more gas. So the total number of gas molecules has to increase by the way the question is worded. Going to number 7. Which of the following gases deviates the most from ideal behavior? And this was a question that was also in the free response answers. I have it here somewhere. Yeah. So we're definitely going to talk about that more because that was also a hot topic on your list of learning objectives that you don't know very well. So we are going to talk about ideal versus non-ideal gases. Make sure to get that in your notes. But for the gist of it, something that deviates from ideal behavior would be a molecule that's really has high intermolecular attractions or is super big. So when I look at these choices here, the first thing that screams out is these are all nonpolar. And I don't think it was this one too. No. Oh. Okay. Well, the first thing I thought was that they were all nonpolar, and so the most massive one would be SO2, and SO2 would have some double bonds and single bonds, so it could be kind of polar. But now that I draw out SO2, I can see that it actually is a polar molecule. Let me show you what that looks like. This is a problem we'll do later. So SO2, S and O. SO2, what it actually does is make a double bond right here with this one and this one. This one goes away. And then there's a coordinate covalent bond that shoots this way. So what it looks like in the end is a double bond this way and a single bond this way. But these lone pairs right here create a polar molecule. So when you have something that's a polar molecule, it is not going to behave ideally. So that means it'll be attracted to other molecules that are by it. And if it attracts to the other molecules, then it's not going to hit the sides as hard because that's like one molecule is moving along and then he's like, oh, this guy's attractive. So he wants to go towards him. And that creates less hit because he's going straight and he's like, oh, he looks good, but he still hits, but he's kind of curving as he hits, so it's not the full force effect. So being attracted to the molecules behind you creates less of a force. So that's why SO2 would be a good one. It's also pretty massive. Higher the volume or higher the amount of space that the actual atoms take up will create a less ideal behavior too, because volume we assume to be negligible for actual atoms, but we know that as you get bigger molecules, SO2 is pretty big, consider as an S and two O's, that volume of the molecule actually takes up space in relative to the whole volume of the container. So it's those two reasons that create different from ideal behavior. Volume of the molecule is pretty big, a massive molecule, or fat molecule, I should say, more than massive, and attraction, being more polar or having high intermolecular attraction. Okay, so number 7, going to number 9. Okay, this is the one I've got on my thing here. Okay, so this is a math one, and somebody did ask, is molarity going to be in there? I guess I don't have molarity in my objectives, but yes, molarity is going to be on the test. It's going to be more in the form, well, of a problem like this, to be honest. I think it'll be more in our reactions unit, which is unit number 4. So you'll see it more often in there. I can't remember why I put it in here. It came up there. Okay. So when we're looking at these ones, 40 mils of 0.25 molar KOH sample. What I found hard about this problem is not being able to use a calculator. It was a little tricky for me. I'm not going to lie. I busted out my calculator to double check my math. I was off. I'm awful at those like point something times point something, like which way did I move the decimal point? I'll be honest, I'm terrible at that. So when I'm looking at this one, I'm trying to find the number of OHs that I have in the bunch. Now something that's tricky about it is this one has 2 OHs. So let's take them one at a time. First, I need to find the number of moles of OHs I have in each of them, because I'm taking KOH and BaOH2 and I'm pouring the two together. So I need to figure out how many OHs is in this guy, how many OHs is in this guy, and then I'll look at the two together. So I'm going to look at how many OHs in this first one. Well, molarity is moles per liter. So what I happen to have is 0.25 molar, 0.25 moles per liter of KOH. And I'm using 40 milliliters, or that's 0.04 liters. So 0.25 times 0.04 is 0.01. Now, I'll be honest, I had to use my calculator for that very part. You might too, because I didn't know which way the zero was. Anyway, my downside, something I would really have to look at before I took AP test. Then if I want to look at how many OHs are here, I've got 0.15 molar, that's 0.15 moles per liter, and I happen to be putting in 60 mils, or 0.06 liters. So if I do that math, 0.009, I screwed up my O's on that one too. You might have done that too. So that's how many moles I have of BaOH2. Now that's not how many moles of OH I have, because for every one of these I have 2 OHs. So I have to multiply this by 2 actually. So that's how many moles of OHs I have. This is how many moles of BaOH2 I have. And for every one of these I have 2 OHs. So that's why I multiply by 2. Now over here, this is how many KOHs I have, moles of KOH. And for every 1 KOH, I have 1 OH. So that really is the number of moles of OH that I happen to have. So now I know how much OH I have from each of them, and I'm going to add them together. So I'm going to take this 0.01 plus this 0.018, and I'm going to get 0.028 moles. And that's how many moles I have. Now I want to figure out the molarity, or the molar concentration. And they're telling me the volumes are additive. That means I'm taking the 60 mils plus the 40 mils. That's going to make 100 milliliters. Or in other words, a 0.1 liter solution, which gives me a 0.28 molar solution. There we go. Tough on the calculator? Completely fair question though the AP could do. I'm just terrible at the calculator kind of ones like this. If you are, you're going to have to work on that. Well, no, you're not, because you're going to get solve-free response. So don't even worry about it. You'll get your calculator. Which means on any of these review things that we're doing, use your calculator. Yeah, don't work so hard. Use your calculator. Okay, number 10. This was the most popular one to get wrong. Which of the following techniques is most appropriate for the recovery of solid KNO3 from an aqueous solution of KNO3? Okay, so I want to go through each one of these. Paper chromatography. What we did with that was we had a piece of paper, or think of like any kind of like piece of paper in general, or paper towel, or like coffee filter. If you put an ink mark on there and then the water absorbs, it spreads the ink. Paper chromatography is going to spread things based on polarity, or chromatography in general, right? Spaces things out or separates them based on polarity. Not what we're doing here. Filtration. Filtration is the thing that is going to take like sandy water. If you take sandy water and you put it through filter paper or a coffee filter, sand will stay on the top and the water will go on the bottom. Filtration is like coffee, taking the coffee grounds out of your coffee. So that's going to take something that's not dissolved. This is talking about an aqueous solution, which means it is dissolved. Titration is going to be able to tell us how many moles of things we have. That's where you have the big burette and you like drip them into there, and you can find a concentration of some unknown solution. That doesn't help us here. Electrolysis is when you have like a beaker of stuff. You stick two probes in there and it shoots electricity into there. You did this in redox. I don't know if Anne actually did it with you. She did a lab. I think she was prepping one. But you shoot two probes in there and you shoot electricity in there, and it forces a reaction to happen that otherwise wouldn't. Like if you wanted to separate water into hydrogen and oxygen, that's electrolysis. Evaporation to dryness, that's exactly what we're doing here. We've got an aqueous solution. I just need to get the water out so I can have the solid left behind. You just got to wait to evaporate it. Or what we did was use the Buchner funnel. Nope, we didn't use Buchner funnel for that. You can't do it for that. Nope, only thing is to evaporate it out, wait for it to dry, put it in the oven. That's number 10. 11. Okay, this one. The most common answer that you said if you didn't get it right for number 11 was A, which is kind of similar, but this is the idea that like dissolves like. So I2 does not dissolve in H2O. H2O is polar, that means I2 must be nonpolar. C6H14, it's all C's and H's, so that's a nonpolar thing. Nonpolar and I2 is nonpolar. Nonpolar dissolves nonpolar. This question is about like dissolves like, which is one of the objectives. So that's why B is the right answer. 12, I got good news for you on 12. That's just a straight up memorize one, right? However, I got two ideas in this one. This one is about the photoelectric spectrum and the idea of like how much energy you shoot in and what happens to molecules when you do that. These are going to be like multiple choice questions for sure. We're not taking a multiple choice test.